A very cool application of the circular restricted three-body formalism gives us something known as the Tisserand criterion. This was originally developed to determine whether multiple observations of a comet were of the same or of multiple objects. You can see the basic issue here. You have something that's traveling from the deep outer solar system and only shows up in the inner solar system once every few decades, or maybe even less frequently. And this object is typically on a very eccentric orbit, meaning that it's interacting quite closely with the sun during perihelion. And that means that its orbit is getting significantly perturbed, and it may not have the same orbital elements after the solar flyby, which means that the next time it comes back into the inner solar system, it might have a quite different orbital characteristic from the one that was previously recorded. However, in the context of a three-body system, the Jacobi constant should remain approximately constant. And so you'll recall, this is our definition of the Jacobi constant, 1/2 the norm squared of the rotating frame velocity of the object with respect to the barycenter of the two primary bodies, minus the rotating frame coordinates x squared plus y squared over 2, minus the quantity 1 minus mu star over r1 plus mu star over r2. And from this, we can write this modified expression for the Jacobi constant that is a function of its inertial velocity and the projection of its inertial angular momentum vector in the E3 direction minus this original potential. If we rewrite these in terms of the orbital elements of the body, we find that this first term has to equal 1 over the distance of the body from the first of the two primary masses minus 1 over twice its semi-major axis. And this term, E3 dotted into H PRLO, will equal the square root of the object's semi-major axis times 1 minus the centricity squared times the cosine of its inclination with respect to the orbital plane of the two primaries. So we can write an expression for negative 2c that is equal to 1 over a plus twice the square root of a times 1 minus e squared cosine I plus 2 times the mu star parameter of the three-body system times the quantity 1 over r2 minus 1 over r1. And these are typically large distances, and so this term is small and can be neglected, which means that the Tisserand criterion can be defined as negative twice the value that we've been calling the Jacobi constant, negative 2c, and will equal 1 over a plus 2 times the square root of a times 1 minus e squared cosine I. The way that we apply this to a comet is that we use the three-body system of the Sun and Jupiter. Body 1 is the Sun, body 2 is Jupiter, our test particle is the comet, and the inclination is the inclination of the comet's orbit with respect to Jupiter's orbital plane about the Sun. The idea here is that given observations of a comet approaching the Sun, it is relatively straightforward using the orbit determination tools that we've already laid out to find its approximate semi-major axis and eccentricity and inclination. From those, we can calculate a value of t, which is often called the Tisserand parameter. If the value of t is approximately the same as that for a previous calculation of another comet, then it is very likely that you are observing the same comet or the same object, because its Jacobi constant is unlikely to significantly change via interactions with the Sun and other non-gravitational effects. Whereas the values of the semi-major axis and the eccentricity and the inclination might not be individually conserved, because these are not guaranteed to be independently conserved quantities in the three-body problem, but the relationship between them is conserved in a pure three-body problem. In modern astrodynamics, the Tisserand parameter and Tisserand criterion is actually an incredibly useful tool in trajectory design. The conditions of the approximation that we just made to define the parameter, that mu star is small and the reciprocals of r2 and r minus r1 lead to small quantities, apply when you're planning deep space flybys. So you can therefore match the semi-major axis, eccentricity, and inclination of your spacecraft pre and post flyby, which allows for very rapid iteration on flyby trajectories. Most recently, the Tisserand criterion was explicitly used in the initial orbital design for the TESS mission, which is in a very cool resonant orbit with the Earth's moon. And for a lot more details in that, you can see these papers by Gengestad and Dijkman. The other really important thing that we get out of evaluating the Tisserand parameter is a quantification of the Jacobi constant of the comet. Remember, this maps to the zero velocity curves of the three-body system. And so in effect, an estimate of C indicates whether or not the particular object that you're tracking is able to enter the inner solar system. Because in order to go from outside the orbit of Jupiter to inside the orbit of Jupiter, you have to have a C value that is greater than the Jacobi constant associated with both the L2 and L1 points of the Jupiter-Sun three-body system. And there was just a beautiful illustration of this in the late 20th century given to us by comet Aterma. This is a long period comet that was tracked once in 1910 and again in 1980. And what you're seeing here is the comet's orbit in the inertial frame. And so you see that here we have Jupiter's orbit. So in 1910, it was spotted outside of Jupiter's orbit, heading inwards. It came in past Jupiter, made a lap around the sun, and then came back out again and was tracked again outside of Jupiter's orbit in 1980. If we plot the exact same thing in the rotating frame, we get what is now a familiar picture. We have motion that bounces off the zero velocity curve associated with the L2 Jacobi constant for the Sun-Jupiter three-body system, and then is able to enter via L2 right near Jupiter. It crosses into the inner solar system through L1, which you will recall is the most efficient way to get into the three-body system. It again bounces off of this contour inside and then makes its way out again past Jupiter. So this intermediate frame is showing the prediction based on pure CR3BP theory. And here it is now overlaid with the actual track. The solid line is the actual track of the comet, and you can see that it matches what the theory predicts to an incredibly high degree. It is an startlingly good model, seeing as how simple it is and how many other effects it neglects. Because this comet essentially had just enough energy to enter through the Sun-Jupiter L2 point, it had to enter the solar system by flying by Jupiter. And so it is worthwhile for us to consider the motion of our test particle in the three-body system as it passes through the space defined by the collinear Lagrange points. Here is another figure from the same paper by Kuhn et al., and it is defining the geometry that we've already found with the collinear Lagrange points, L1, L2, L3, and the off-axis Lagrange points, L4, L5, at 60 degrees, leading and trailing our secondary body in the three-body system. And we can draw, as we have been, the contour associated with the L2 Jacobi constant value, which has this form and opens up this neck between the outer system and the inner system that connects L2 and L1. We can do some more detailed analysis about the motion that is happening in this region, but to do so, we need to define a new tool, and that is the invariant manifold. Here's the basic idea. If you start your motion at a Lagrange point at, say, L1 or L2, these are equilibrium points, and so if you're exactly on that point, you will stay there forever. However, we know that these points are inherently unstable, and so perturbations will cause you to move away. The collection of trajectories carrying you away from a Lagrange point are known as the unstable manifold of that Lagrange point. Similarly, the collection or bundle of trajectories that carry you to that Lagrange point are known as the stable manifold of that Lagrange point. And we can find these manifolds explicitly by investigating the eigendecomposition of the Jacobian partial of z dot with respect to z, where the vector z is defined as the state of our three-body system. Z is the collection of coordinates x, y, z, and their first derivatives, where these are the rotating frame Cartesian coordinates of our test particle with respect to the barycenter of the two primaries. So if we evaluate the Jacobian, what we get is a matrix of the form that is, we get a block matrix where the first block is a 3x3 zero matrix, the second block is a 3x3 identity matrix. This third block here are the partial derivatives of x double dot, y double dot, z double dot given by our previously derived equations of motion for the system with respect to the coordinates x, y, and z. And this final fourth block has the form 0, 2, 0, negative 2, 0, 0, and 0, 0, 0. And again, I urge all of you to convince yourself that this is correct. The spectrum of this system, the eigenvalues of this Jacobian, it consists of two pairs of imaginary eigenvalues and one pair of real eigenvalues, again, necessitated by the structure of this matrix. The eigenvector corresponding to the larger real eigenvalue is the unstable direction, and we will call that VU for unstable. So again, VU is the eigenvector corresponding to the larger of the pair of real eigenvalues. The other real eigenvalue corresponds to the eigenvector Vs, which is the stable direction. So what do we do with this? Well, let's define Zu as the sum of Z plus or minus some small quantity epsilon times Vu. If you propagate this forward, if you take these Zus to be initial conditions and propagate them forward in time, you will get your unstable manifold. You will get the bundle of trajectories carrying you away from the associated eigenvalue. Similarly, if we define Zs as Z plus or minus epsilon times Vs, and then we propagate this backwards in time, you will get all of the things flowing in towards the Lagrange point, and therefore you will get your stable manifold. We can do this exercise not just for the Lagrange points themselves, but also for these stable structures that we have previously defined for the Lagrange points. So all of the stable structures about L1, L2, and L3 each have stable and unstable manifolds themselves, which is described in enormous detail in Kuhn et al. 2011. So if we pop back to the visualization of this, this gives us a very intuitive understanding of what is happening when a body passes from an outer system of a three-body system into the inner system of a three-body system by way of this neck formed by the L2 contour. The body is traveling along a stable manifold of the Lagrange point, or an associated stable structure of the Lagrange point, as indicated here by the Lyapunov orbit. The body then hops onto the unstable manifold of the structure. It travels towards the secondary body of the three-body system, hops onto the stable manifold of the L1 structure, passes through that onto the unstable manifold of the L1 structure, and then flows into the inner system. And then on the way out, it repeats this entire process in reverse. This is an incredibly important addition to our trajectory design toolbox. The ability to find these manifolds and find initial conditions that map us to motion along these manifolds means that our spacecraft can hitch rides for free in multi-body systems. And this is particularly useful in moon tour design, or the design of spacecraft trajectories in the very, very low thrust regime in the Earth-Moon system, or the Jovian system, or the Saturnian system, and so on. Whenever you have multiple bodies, you can take advantage of this. And of course, the Sun and Jupiter form the largest, in terms of mass, three-body system in the whole solar system. But unfortunately, the distances are very large. This all works out beautifully for comets, but recall that comets take decades or centuries to get where they're going. We can't be that patient with our spacecraft. So even though you can define all of the same things for interplanetary transfers, you can ride these stable and unstable manifolds of the Sun Jovian system from the inner solar system to the outer solar system. It just takes too long. So for now, that's not incredibly helpful in terms of mission design, because if you wanted to take advantage of it, you would have to wait for decades. And we just don't want to wait that long. On the other hand, if you're talking about designing something hyper efficient in the local Earth-Moon system, or in the Jovian, Saturnian, Neptunian, Uranian systems, et cetera, where there are lots of moons to take advantage of, then this stuff is great. And it leads to some really beautiful trajectories. For our last application of the circular restricted three-body problem dynamics, we will take a closer look at L1, the Lagrange point lying between the two primaries M1 and M2. We will define a parameter gamma 1, which is going to be equal to the distance between L1 and the second primary M2, which allows us to write the position of the Lagrange point L1 with respect to O, the barycenter of M1 and M2, as 1 minus mu star minus gamma 1 in the E hat R direction, the radial direction of the rotating frame defined by the three-body system. Recall that for the on-axis collinear Lagrange points L1 through L3, we have a third-order polynomial that describes their location. Substituting in our newly defined gamma 1, we can write negative the quantity 1 minus mu star minus gamma 1 is equal to negative 1 minus mu star times 1 minus gamma 1 all over 1 minus gamma 1 squared plus mu star over gamma 1 squared. Now, let's assume that gamma 1 is much larger than mu star. Well, then we can rewrite this expression as that is, the mu star term in this side can be thrown out because it's much smaller than gamma 1. And so all that's left is gamma 1 minus 1. And on this side, this term becomes negative 1 plus 2 gamma 1 plus terms of order gamma 1 squared. And we have still mu star over gamma 1 squared. And that means that altogether, we can write gamma 1 cubed is approximately mu star over 3, which also confirms that in this case, gamma 1 is much larger than mu because mu goes as gamma 1 cubed. We use this to define a radius, which we call the Hill radius, which is given by mu star over 3 to the 1/3 power times the separation between masses M1 and M2. The Hill radius defines what is known as the Hill sphere. And what this is a very approximate definition of the region of stable orbits about a body in the presence of a perturber. As we go along, we're going to add a couple more definitions that are similar to this, but all of them have different sets of assumptions behind them. What the Hill sphere specifically is telling us is the approximate region in space about a body, so for example, say about the Earth, in which orbits will be long-term stable, even though the sun is acting as an external perturber in the sun-Earth orbiting body, three-body system.